All right. I'm trying to connect so that you can have a reward. You can come back. So in the last class, we ended in talking about homologous series and said that each member of the series is called a homolog. And we had an assignment. Today we're talking about isomerism. Now I want you to be attentive because I'm going to be a little bit faster than before. Because at this stage, you guys are not big students. Isomers are like twins. So when you talk about isomerism, you're talking about two things that are similar, but they have a little difference. So isomerism is a phenomenon whereby a compound has the same molecular formula and different structural formula. That's why we talk about structural isomerism. So in isomerism, when we talk about isomers, we are talking about twins, like I said. And we have two types of isomerism. The twins can be by structure or by stereo. So we have structural isomerism and stereoisomerism. In structural isomerism, the same molecular formula, but different structural formula. Just like you have a twin, they have the same molecular formula because they're of the same age. But their structure, one is taller than the other. We call them structural twins. Then in stereoisomerism, are not identical. They are the same age, but one is male and the other one is female. So they occupy different positions in space. We talk about spatial arrangements. So their position in space differs. So same molecular formula, but the atoms occupy different positions in space. Now, in chain isomerism, we have one having a straight chain and another one having a branch chain. They have another one is position isomerism. How are you? Your life is good. Please hold on, 5 seconds, hold on. Sorry, I had to attend to the emergency. Then, now, if in isomerism we have two types, structural and stereo. In structure, we have chain isomerism. They are the same carbon, the same hydrogen, but one is on a straight line, the other one is on a branching. I forgive you. Another one is position isomerism. The same number of position 1 to 2. Like if it's something like alcohol now, then the green ball becomes hydroxy group. So that hydroxy group is moving from position 1 to position 2. So we can call it, because it's 4, we call it boots. So no characters, they behave differently. Butan 1-ol is a primary alcohol. Why butan 2-ol? Why butan 2-ol is secondary alcohol. So in that case, the position of that hydroxy is one of the substituents, which can be a functional group, is going to change position. So making the compound a different compound. Another one is functional group isomerism. In functional, now if you look at this, the one that is ash is hydrogen, the black one is carbon. So this oxygen is on carbon number 1. Is in carbon number 1 on the first structure, and in second structure is in the middle of them. Now, in that first carbon, we can call it alcohol. But in the second carbon structure, we are calling it ether, because it's like oxygen is in the middle. So functional group is when there is a change of one of the atom, it moves from one functional group to another. So because of the oxygen has been changed, we move from alcohol to ether. We can also move from, when we go in detail, we're going to see how we can move from aldehyde to ketone. So functional group isomerism is when the functional group of a compound changes because one of the atoms has been changed. So the same, if you look at it, the same number of carbon, same number of hydrogen, same number of oxygen. But because this oxygen has changed position, we're having another functional group, making it functional group isomerism. So these are the 3 types of chain isomerism that you should know. We have chain, we have position, we have functional group. There are others. That's one they call metamerism. But those ones, at this level, these 3 is the most common. Then when you come to stereoisomerism, we are talking about geometric isomerism and optical isomerism. Geometric isomerism is the one that is most common here, which is where we have cis and trans. In this isomerism, the position of one of the atoms makes the compound to change in identity. Well, we have now, because one of the substituents, when both substituents are on the same side, we call it cis. When they are on adjacent side, we call it trans. Now, in terms of stability, can you realize that the one that is on adjacent side is more stable than the one that's on the opposite side? So in terms of performance of this compound, because of the position of this substituent being on the same side and this one being on adjacent side, their identity and properties changes. So that's what we call them isomers. Everything is the same, but because of position of these atoms, it changes the identity of this compound. Now, when we talk about optical isomerism, we are talking about mirror images. Mirror images is when you look at yourself in the mirror, your right hand becomes your left. The mirror images. So in optical isomerism, we are talking about mirror images, and we're also talking about chiral center. Chiral center is a center where a carbon is connected to 4 different functional groups. Just for you to know the advanced aspect of chemistry. Like I said, when a compound have the same molecular form, structural isomerism, which is arrangement that are different in spatial arrangement. Some are on straight chain, another one is on branch chain. And remember, in terms of properties, they differ. Because they're going to have similar chemical properties, but not similar. They're also going to have slightly different. The one that is branch, the branch one is going to have a lower boiling point and the lower the melting point, because the branching already, they are crowded already. So being crowded, they're generating heat itself. So when there is small heat, the boiling point, the solution can easily boil because they are crowded. But the one that is spread apart, it takes time for the heat to cover everywhere because there is a distance between them. So that branch chain has lower than straight chain. So that's some of the physical properties that changes in chain isomerism, the straight chain and the branch chain. That is what we have in chain isomerism. Then after chain isomerism, we have position isomerism. Remember, like I said, the position of one of the functional group can change the identity of that compound. Then in that case, they have similar chemical properties and they're going to have slightly different physical properties, but their chemical properties are always similar because they're the same group of compounds. Then the next one is functional group isomerism. Because they have different functional groups, they have different chemical properties, they have different physical properties. There's nothing similar about them. So that's what we'll talk about functional group isomerism. Questions at this stage before I continue. So this is an example of structural isomerism. We have butane and we have 3-methylpropane. My butane is carbon number 4. And my 2-methylpropane is still carbon number 4. But because one of the carbon has been used to form a branch, we call it a chain isomerism, from straight chain to branch chain. Now, if you look at these in their properties, they show similar chemical properties because they are on the same functional group. Because the functional group is still the same. It's still the same saturated hydrocarbon. So their physical properties are going to differ because of branching and straight chain. The more they branch, the lower the melting points and boiling points. So that is the difference between them. Now look at the position isomerism. As 2-chloro. Because if I want to name, when I follow my right, that 3-chloro becomes 2-chloro. So the only thing we have here because the compound is saturated from anywhere. Do you understand that? So I cannot have 3-chloro in this compound because if that 3-chloro from my left is 2-chloro from my right. So that's why we have to position isomers. We call them position isomerism. This is another position isomerism. You can see in a cyclo compound, we have this is a benzene that has 2 substituents. It can either be 1, 2, 1. In benzene, we call it auto, meta, and para. 1, 2 position is called para. These are called position isomerism because the position of this substituent changes the identity of this benzene. So, in terms of chemical properties, they can be similar. So, physical properties, there must be some similarities and differences. They are not the same. If you remember, I said functional groups are not. Okay, fine.
The network is not good.
Network.
We can't hear you very well.
Yeah. Network is even me. Can't you see it's logging me out? It's logged me out several. I don't like it. With the frequency we are flowing, never loved to be interrupted. Nobody can sign it. You don't know how to write a letter. There's no place for HOD. There's no place for court advice. It's not how they tell you to write letter.
You just say
No. How to write letter? Write to director CITS through the chemistry. Through course advice for 300 level chemistry. That's how to write all official letter. I think I need to check position. This is not my frequency. Now we are talking about functional group isomerism. I said from one functional group to another. Everything about the isomerism. So I can move from alcohol to ether, from aldehyde and to ketone. Remember, aldehyde and ketone, they have something in common, carbonyl. If time permits us, we're going to look at them individually. Then we're going to have acid and ester. And if you want to learn more about all this, when you go to my YouTube channel, you can see video made on alcohol, on carbonyl compounds. So for the essence, for you to have idea of what they are talking about, so that when we are talking about aldehyde turning to ketone, you will understand. So it's very, very important. Mini class. Mini class. Let me finish this class. Go and drop it. Mini class. Now, alcohol and ether. Now, alcohol, example is the ethanol. When this ethanol changes position, it becomes methoxymethane, which is an ether. Because of change of this position of oxygen, alcohol become ether. So they have formed another functional group because alcohol is a functional group, ether is a functional group. So that is that aldehyde and ketone. Now that black is carbon. The orange color is oxygen. Carbon connecting to oxygen is called carbonyl. So when these carbonyl are at the terminal, they become aldehyde. When they're in the middle of the compound, they become a ketone. So that is why, because of the position of this functional group, we are having different class of compounds, aldehyde and ketone. They behave differently. In terms of their reactions, they are different. So that's what we call functional group isomerism, which is example of structural isomerism. Carboxylic acid and ester. If you look at carboxylic acid, the carboxyl functional group, like we saw in functional groups, are COOH. Now, look at that COOH. If you look at the COO coming from the terminal to internal, becomes ester. Terminal is an acid, internal is an ester. So it's still the same COO, but because of the position of the COO, gives us another functional group. Because carboxylic acid is a functional group, ester is another functional group. So that's why we have functional group isomerism. In stereoisomerism, like I said, we have the same molecular formula, but different spatial arrangement. The arrangement in space differs. If you come to geometric isomerism, we're going to have them being either on the same side or on adjacent side. What we're looking at is this ball that bears green. When they're on the same side, we call them cis. When they are adjacent side, we call them trans. And remember, for a compound to undergo geometric isomerism, it must be alkene. There must be double bond. Now, that double bond is what restricts rotation or movement. Unlike the saturated compound, that has no double bond, there is no restriction. I can move from anywhere. That is why we are talking about this particular compound. Let me go back. That's why I said that this compound cannot be 3-chloro because there is no restriction. So my carbon 1 can be from my right or from my left. So I cannot say carbon 1 must be from my right. But assuming there is a double bond, that double bond will give me an idea of where my carbon 1 must be, because double bond must be given a preference in my naming. But because there is no double bond, I can start from anywhere to give my carbon 1. There's no restriction. So in that same manner, in geometric isomerism, because of double bond, there is restriction. in rotation, in movement. So the one that are on opposite sides cannot become an adjacent side. They must maintain where they are. So that's why we have two isomers, which we call cis and trans. Cis on the same side, trans on adjacent side. And this cis is represented by Z. Whenever you're reading organic chemistry textbook and you see a place where they use Z, it means they are talking about cis. And whenever they use E, they are talking about trans. These are isomers, they are twins. But because of the position of one of the substituents, it changes the identity of the compound. And this must happen for the compound that has unsaturation of alkane. It cannot happen in alkyne. It can only happen in alkene, double bond. Because of that restriction in rotation, like now, look at, there's restriction is carbon-carbon double bond. There's no restriction in carbon-carbon single bond. Single bond, like we said in the other compound, is not restricted. So that's why I can start from anywhere. But when there is double bond, there is restriction. Restriction is giving me that you can't go beyond this. So there must be a pattern that follows. But when there is no double bond, there is no restriction. We are still saying the same thing, cis and trans. When substituents are on opposite side, remember these substituents are compounds that are not hydrogen. Hydrogen cannot be regarded as substituent. So if you look at the structure, those ones are written in ash are the hydrogen. But the one in green is a substituent. The one in black is carbon. So for you to understand. So when there are substituents, the substituents can also be any other thing, can be methyl. So look at the other two. The first two, we have a substituent, which is something like oxygen or any other substituent, and methyl. So, but the other ones are methyl. So the substituent must not be a compound like chlorine. It must not, like the other, this green might be chlorine. So it must not be something like chlorine. It must not be something like bromihalogen. It can also be methyl. Methyl is CH3. It's a substituent. Remember, when the assignment I gave you, I said alkyl substituent. One of them is methyl. So whenever methane loses hydrogen or alkane loses hydrogen, become alkyl. So they are called substituents. So these are what you saw. Whenever you see black connected to 3, that is carbon connected to 3 hydrogen. So that's what they call alkyl. So it can be, when you see all carbon connected to 1 hydrogen, it's carbon hydrogen. So whenever you see carbon connected to 3 bonds, it's methyl. So for you to understand what is being done. But in the exam, you're not expected to use balls. You're not expected to use balls. You're expected to use carbon and hydrogen. So the assignment I'm going to give you today, you're going to use carbon and hydrogen, not balls. Balls is just to make it easier for you to understand. So I think that's the end of the class. So in today's class, we're able to learn about isomerism. And in isomerism, we have 2 types of isomerism. We have structural isomerism, we have stereoisomerism. In stereoisomerism, we have optical and we have geometric isomerism. Please, can you mute everyone? Can you mute everyone? So, and we talked about that in 10 Please, can you mute everyone? Please, whenever you come to class, mute yourself. Don't expect somebody to mute you. We are dealing with senior students. We are not dealing with kindergarten. Please. So, I'm trying to do a recap of the class. In an exam, or if you're asked types of structural isomerism, with an example, don't give me one example. Every example you're giving on this is 2. If I want to talk about chain isomerism, I must use two structures. One telling me that straight chain and branch chain. If I want to talk about position, I need two structures. So, and understanding what you're giving. Don't just write structure without giving us name. That's some of the things you have to know. You have to know how to name these compounds. Now, we have two types of isomerism. We say structural and stereo. In structural, we have chain, position, and functional group. In stereo, we have geometric and optical. That's all we talked about today. And the assignment you're supposed to go with is number one, right? Define structural isomerism. Kostrep, are you writing?
Yes, ma'am. Yes, ma'am.
Define the following terms. Number one. Did I give you definition last time?
No,
The
ma'am.
last assignment.
No, ma'am. No,
No, you
ma'am.
don't give us definition. You just give us to.
Okay. So define the following terms. One. Molecular formula. Empirical formula. Homologous series. And structural isomerism. Define the following terms. One, molecular formula. Two, empirical formula. Three, homologous series. Four, structural isomerism. Taking?
Yes, ma'am. Taking.
Question 2. With one example each, list the types of structural isomerism. With an example each, list the types of structural isomerism. Taking?
Taking.
Yes, ma'am.
The third and the last. With example, show the types of geometric isomerism. With an example each, show types of geometric isomerism. So, any question on the assignment? So I gave you 3 assignments. Tomorrow should be the deadline.
Sorry, for the last one, ma. For the last one, we did not get it.
With an example each, show types of geometric isomerism. Remember, example, I mean, is structure. Anything we are talking about example, it needs a structure. So, with an example each, show the types of geometric isomerism. How many types of geometric isomerism do we have?
2.
Huh?
2, ma. 2.
So name the 2 and give me an example.
Okay,
ma. Hope assignment is well understood.
Yes, ma'am. Ma,
Okay, question.
I would like you to help me to do a recap on that difference between position and functional group under structural isomerism.
Okay. Position is like if I have alcohol,
Yes, ma'am.
the same hydroxy group is in position 1. And that same hydroxy group, I bring it in position 2. Position 1 will make it, assuming my alcohol is butanol. If it goes to position 2, it becomes butan 2-ol, right? butan-1-ol and butan-2-ol is the same alcohol. The functional group has not changed. It's the same alcohol, but the only thing, their position have changed from 1 to 2. So we call them position isomerism. If I have chlorine, chlorobutane, my chlorobutane will be on position number 1 or position number 2. Because it's still the same chlorine, it's changing position. It becomes what? Position isomerism. But in functional group isomerism, assuming I have alcohol, and in that alcohol, my oxygen changes position, move from 1 and left hydrogen alone and come and be in the middle of the carbon. It changes from alcohol to ether. In position, the whole oxygen and hydrogen is changing position. But in functional group, one of the atoms might change, or 2 of the atoms will change position. Do you understand? Now, let's go to the functional group. Now, if you look at the first one, alcohol and ether. In that alcohol, my oxygen of ether moves from being at the terminal to being in the middle. Change of functional group. But in positional isomerism, that oxygen can move from one to another. Now, if I want to do positional isomerism, I cannot use this small 2 carbon of alcohol. In position, I can use minimum of 3, which I can have 1 or 2. But in this issue of functional group, I can use 2, because in the other one, I want to put oxygen in the middle. Do you understand me? For alcohol. So I cannot use ethanol for position isomerism in alcohol. So I cannot use anything X. Whenever I want to use positional isomerism, I can use minimum of 3 carbon. Because if I use 2 carbon, by my right, carbon 1 is the same thing, carbon 1 by my left. So I cannot have anything like position isomerism with 2 carbon. My position isomerism starts with minimum of 3 carbon. But in my functional group isomerism, I can use 2 for alcohol, because either I form ethanol or methoxymethane, forming an ether. So in functional group isomerism, when I change one of the atoms or group of atoms, I'm going to form another functional group. While in position isomerism, they are changing position, but they are still the same class of compound. I'm not changing compound. I can talk about, this is a haloalkane. 2 bromo, 3 bromo, but it's the same bromo. So they are the same family. They are not changing. But when I'm changing, I'm forming another functional group. It becomes functional group isomerism. Is that taken?
Yes,
Is
ma'am.
it clear?
Thank you. Yes, ma'am.
Okay.
Thank you, ma'am.
Another question. Who else have question? Oh. No other question.
Mr.
Yes,
Sanko, if you are raising your
yes,
hand.
ma'am. Yes, ma'am. Good afternoon, ma'am.
Good afternoon. Ask your question.
Yes, and it actually with regards to structural isomerism. I want to know, for instance, in real life application, are we saying, can we say the production of fuel or petroleum chemicals, and then the pharmaceutical industry can make use of a structural isomerism? Are we in real life situation? The production, like fuel production. And then
see, structure. If I see propanol,
yeah,
and I see propan, I cannot use propan-2-ol. Not going to give me the same product I'm looking for. So as a chemist, if you go to a shelf and what you want to use, like you want to do production now, what you want to use to bring to produce your drug is propanol. It is wrong for you to go and use propanol because you're not going to get the same thing, but they are in the same family, but they cannot do the same reaction. Chemicals are unique on their own, even if when their name seems similar. So the position of one of the substituents changes the identity and character of that particular compound. They can't be the same. So that's the essence of that. So now if you're told to produce and you produce a propan 2-ol and give it propan 1-ol, you spoil that production. That mistake is going to cost a whole lot. So you have to be careful to be religious in whatever you're producing and what you're labeling. So that's why as a chemist, labeling is very important. Whatever you're doing, label it well, because wrong labeling can destroy a whole lot. Can even destroy a badge of 1 billion naira just because of one simple mistake. So that's what we're talking about. Exactly.
Yes, ma'am. Yes, ma'am. Thank you.
Yeah. Any other questions? I apologize for what happened on Tuesday. This thing would have finished it on Tuesday. Today we're supposed to start another class. So all this one we have been dragging. So this time around, I have to increase my pace. My lectures in Unilag by now, we are preparing for exams, so I will have time. So on Tuesday, we're going to optimize our 2 hours complete. So come class early. As soon as it's 5 minutes, as soon as I come online, I'll start. When I see one person or two persons, I can't be wasting time because there's no time to waste. Because my class, I normally finish before time. So we can have to do revision. So I don't want to slack with your set. So let all right. Thank you very much. Are there any other question? Okay, me. Joanne, ask your question.
Good afternoon, ma.
Yeah, good afternoon.
Ma, please, some of us, we did chemistry labs very, very many years ago, more than 20, 25 years ago. And coping with this fast lecture is somehow, can you please slow down for us? Maybe, I don't know, the class is so fast. I don't know how you can assist us.
Do you not understand it? How can we? Okay, don't worry, you're going to have access to the notes. I'm going to share the note with you. I'm going to share the slide with you, and I'm going to have a recorded version of this note. Just my time. Now that I'm done with my lectures here. So take time to do recorded version of this particular class on YouTube so they can go and listen to it all over and over again. That's what I want to do. And I'm going to share the slide with you. As soon as I'm finishing this class, I'll just share it. So I don't forget. Any other question? Well, the truth is that after this class, like I'm going to share the slide, I expect you to go through the slide and ask your question. I'm always available to answer your question. You'll be fine. You'll be fine. By the time you'll be fine. Take you back to class, even when you're not in class, So you still hear the voice again. So by unconsciously. So that's the essence of the class. Okay. So you'll be fine. Any other question? Okay. Yes. Is in that problem. So what you need to do? So direct get yes through the I got help you. You know what to prepare the So is there another question? Let me end the class. Leave my students are disturbing me. So if there's no other question. So for any other question, you can also ask me on my private page. All right. Thank you very much. So see you on Tuesday.
Thank you.
Thank you, ma'am.
Thank you.